Hey guys, welcome again to QSO 520 Management Science and Spreadsheets. And today we are looking at the topic which is integer linear programming. What does it mean by integer linear programming? Integer linear programming means that all decision variables are restricted to assume only integer values. Many business decisions or problems need integer solution. For instance, if we are to look at the optimal number of labor, so there is no fractional number of labor or workers. So let's say if we need 5 employees, then there should be 5 employees, not 5 point. We cannot have the fraction of employees. Up to this point, we haven't focused on the integer situation, and the approach that we have been using is known as relaxation approach. The relaxation approach ignores integrality condition. So we are going to look at this problem, which is ABC company problem, and see if we need to apply the integer linear programming or we don't have to. And so the problem says that ABC company sells two models of summer pools. One is the plastic pools, and the second one is the metal frame pools. And the company produces and install a common water pumps and appropriate amount of tubing. So each plastic pool produced requires one pump, 9 hours of labor, and 12 feet of tubing, and contributes $350 to profit. On the other hand, each metal frame pool produced requires one pump, 6 hours of labor, and 16 feet tubing, and contributes $300 to profits. So assume the company has 200 pumps, 1,566 labor hours, and 2,880 feet of tubing available. And so we are required to create the linear programming problem where X1 and X2 represent the number of plastic pools and metal frame to produce. So our decision variables, the pools cannot be in fraction. And so in this case, we will try to see if we need to apply the integral condition or if we don't need. And we will apply integral condition if at all the results will give us the fraction of the decision variables that are not supposed to be in fraction. And so we will start with the relaxation approach, and then we'll move on to the integral condition. So we're going to create our model and use solver to solve it. So here we have ABC company. So the first thing to do is to decide on the decision variables. And we are given two decision variables. We're given X1 and X2. One is for the plastic pools and the other one is the metal frame. And the second thing is to define the objective function. In this case, we're talking about the profit, and so we are maximizing profit. And so in this case, we are maximizing profit. So we're maximizing profit that we can get by selling these products. And so we'll say max. Here you can see that the plastic pool will contribute $350 to profit, and the other one will contribute $300 to profit. That is each of this. So we can say we are maximizing 350 X1 plus 300 X2. So that's our profit. Right here, profit. And then the next thing is to find constraints. And so we can say subject to constraints. And in this case, we have a number of constraints. So you can see that here it says each plastic pool produced requires 1 pump, 9 hours of labor, and 12 feet of tubing. And that's just for the plastics. And then if you look at the metal frame pool, it requires as well 1 pump, 6 hours of labor, and 16 feet. So we can put all these constraints together. And so here we have 1 pump and the other one is 1 pump. And so we have 1x1 plus 1x2. And then we have the 9 hours of labor and 6 hours of labor. So we have 9x1 plus 6x2. And then we have 12 feet of tubing. And here we have 16 feet of tubing. So we'll write as well 12x1 plus 16x2. Now we're going to see how much are we limited by the number of pumps or labor hours and the tubing. So you can see that the company has 200 pumps, and so this is the only amount they have. And so we can say that we can put equal or less to 200. And let's see the number, the labor hours. And so you can see we have 1566 labor hours available. And so in this case, we can also put less or equal to 15 labor hours. And finally, we have 2,880 feet of tubing. And so in this case, we can say less or equal to 2880. This is pump constraint. And the second one is labor constraint. And finally, we have tubing constraint. So the second set of constraint is non-negativity condition, where x1 and x2 are supposed to be greater or equal to 0. And so we'll say that this is non-negativity condition, but we're going to add the condition with, or the integral condition. And so we'll say x1 and x2 must be integers. And so this is integrality condition. So you can see that in this case, we are adding this condition which we didn't apply before. But as we said, we will start with the relaxation approach that will ignore integer condition until when we find that we are limited with the results. This example is actually a direct one, and therefore it's not really complicated. It's an easy one. So, well, having this mathematical model, then we can now apply this into the model that we can use solver to solve it. So here we have ABC, and the company is producing pools. And so the company will produce plastic and also the metal. Or we can say X1 and X2. So let me put this X1 and the metal. We can say X2. Then we want to see how many products or the number of products that this company will make. So we are looking at the number to make, and that it will be for the plastic and for the poles. And so in this case, we have no idea how much we should make, and so we can just put zeros. And so this will be our decision variables. So let me highlight this to indicate that these are the decision variables. They can change. We can now add here unit profit. And remember, our unit profit is $350 and $300. And so we have $350 for X1 and we have $300 for X2. So we can look at the total profit. Let me write here. And so we can find our total profit. And in this case, our total profit will be objective cell. So the total profit will depend on the number of poles to make. But we know that the unit profit is 350 for X1 and the unit profit for X2 is 300. And therefore we can apply the Excel function. So just put equal sign and then sum product. And in this case, we are going to select the unit profit and put comma sign and then select the number to make. And so close the bracket and enter. So at this time, we are not producing anything and therefore our total profit is 0. But the profit will change as we are going to vary the number to make. The next item is to look for the constraints. And our first constraint is the number of pumps that will be used. And the second one is labor hours. And the third is tubing required. So we need one pump for a unit of X1, and also we need one pump for a unit of X2. And the labor hours, as we have explained here, will be 9, and then we have 6. And the tubing required, we have 12 and 16. So we have 12 and we have 16. We are going to use the resources, so use the resources. So used resources will depend on the number of X1 and X2 to make. And so we will put equal sign and put Excel function, sum product. And we are going to select the pumps and then number to make. However, labor hours will also depend on the number to make and tubing as well. So we are going to lock down these cells C22 and D22. So all you have to do is to just put the $sign, and you can put your mouse here. And because I'm using Excel, I will hold down function and F4, and so that will give me the $sign around C cell, and also I'll do the same for D, where I'm going to hold down function and F4, and so that will put the $signs. And then we can now close the bracket since we know that these values are locked, and so we can enter and we can copy the formula to the other constraints. Since we know the use of resources will depend on how many resources are available, so we are going to put limits. And if you can remember, we have these limits. And so we're going to put them here, less or equal to 200, and then we'll copy this because they look the same, and that will be less or equal to 1566, and the last one will be 2880, and these are the constraints, or yes, these are the constraints. The next item is to put the non-negativity condition, and so here we have x1 and x2. So I'm going to type x1 and x2, and the limits for x1 will be greater or equal to 0, and so the same with the second, or the x2 should be greater or equal to 0. But we need to find what is x1 and what is x2. So just put the equal sign and click the amount to make. So any amount that we're going to make should be greater or equal to 0. So you can put equals, you can click enter, and in this case we have 0. So if you change and put 3 there, then this will also change. Now let's put x2 as well. You can put equal sign and just click on this, the number to make for x2, and enter. And so at this time we have only, we haven't produced anything. So if you put 1 there, you can see that this will also change. Let's bring this back to 0. Now we can use Solver to solve this problem. And because I'm using Mac, I can go to the tools and Excel add-in so that I can add Solver. It's actually there. So if I click on the data, then the Solver is there. And so just as we did before, we are going to look at the set objective. And so we have to look at the objective cell. So I'm going to click on it. And then we need to maximize our profit. And that's what we have. And we are going to look at the changing variable cells. So I will highlight these two. And that will be subject to the constraints. So we are going to add constraints. And our first constraint will be the used resources that are less or equal to the available resources. And so I will select these used resources, and they should be less or equal to their corresponding availability. And then we can add, at this time we're going to add the non-negativity condition. And so we'll select these values, and they should be greater or equal to their corresponding values, which are zeros. And that's all with the constraints. And so we can click OK. And we have to make unconstrained variables non-negative. And instead of GRG non-linear, we are going to use simplex linear programming, and so we can solve. So all constraints and optimality conditions are satisfied, and let's see our results. As you can see, our decision variables are integers, and so they have satisfied the condition, and so we don't really need to use the integral condition in this case. So we can actually stop here, knowing that we will be able to maximize our profit which is $66,100, and we can maximize our profit by producing 122 of X1 and 74 units of X2. And in this case, we'll be able to utilize all the pumps, which are 200, and also we'll be able to utilize all the labor hours and almost all the tubing required. We can click OK, and let's copy this, copy, and then just paste somewhere else, but just paste special without the formulas. So we're going to paste just values, and so we can keep these results. Now we can go back here and do some changes. And so let's go back to the questions or to the problems. And here we have problem number 2, which says, assume that for the next production cycle, the company has only 1,520 hours of labor and 2,650 feet of tubing available. And we're going to maintain just the amount of labor. And so we are supposed to create the integral linear programming problem and find the integer optimum solution. If we go back to our model, the only thing that we need to do is to change resources available in terms of labor hours and also in terms of tubing. So we have 1520, here we have 15, and also we have 2,650. Because we have changed this, then we are going to run solver again to see what will be our results after we have expanded the resources. And so we can go back to the solver, and we are keeping everything. So we have the total profit, we have also the changing variables, and they're going to change according to the constraints available. And we will keep the constraints the same because all we have changed are just these two constraints. So we are going to solve, and you can see all constraints and optimality conditions are satisfied. And so if you can see, the number of tubing or the number of poles to make are in decimal, they are not integers. So you can see that for X1 we have 116.9, and here we have 77.9. So we cannot have non-integer production of these two products, and so we need to make this integer. So you may think that we can round them up or we can round them down. And so let's start by rounding them up, because here we have 116, so we could make 117. And then this one, instead of having 77.9, why don't we have 78? You can see that the labor hours needed will be more than the available labor hours. And so the tubing required will be also, the tubing required or used will be more than what is available. So this actually will not be applicable. We cannot utilize resources more than what we have. And therefore, by rounding them up, it won't give us some good results. Now, let's try to round them down. And so here we have 116.9, so we just maintain 116. And let's say just maintain 77. And in this case, you can see that we are not utilizing all our resources effectively. So it is not advised to round this up or to round them down, but we need to apply the integrality condition. We can go back to solver to make sure that we are going to make these two integer values instead of rounding them down or rounding them up. So to solver, and all we need is to add one more constraint. And so we're going to add the integrality condition. And so we are going to select the number to make for x1 and x2. And those two, in fact, we could also highlight them here, but we can highlight these two, and you can drop down and select integer. And so that means those values should be integers, and click OK. Now we have added that one constraint. However, you need to go to options to make decisions on how that integer should look like. We are going to see the required fluctuation from what we have. So here we are looking at the percentage that can be allowed. So should we allow up to 5%, or what do we need here? So first of all, don't click here, because when you click, you're going to ignore integer constraints. But please uncheck this and just make this to be 0, very close to the best value we can get. And so make sure that you put 0 there, click OK. Now you can go to solve. Here we have all constraints are satisfied, which is good. And you can see that we have our integral or integers. All our decision variables are restricted now to assume only integer values. And so we have 118, and also we have 76. And in this case, we're almost using all the pumps, almost, just 6 left. We also utilized our labor hours, almost all of it. And we have used a big number of the tubing. So this is how far we can go. This is the best decision towards maximizing our profit. And that's how we can apply integral condition.